Okay. So today we will discuss about the reversible and irreversible process. Okay. So yesterday we have completed first law of thermodynamics and second law of thermodynamics. So to recap, first law of thermodynamics is nothing but conservation of energy. So heat input is equal to internal work increase in internal energy plus work done. Okay. So we have studied about different processes like isothermal process, adiabatic process, isophoric process, isobaric process. So those are different processes we have discussed while studying about first law of thermodynamics. Okay. Then we have studied about work done in different types of processes like isothermal, how much is the work done, adiabatic, how much is the work done, in isothermal, how PV is equal to constant because the ideal gas equation PV by T gets converted is constant now become PV is equal to constant because T is equal to constant in isothermal. Similarly, with the help of integration EdV from V1 to V2, we have got the work done both for isothermal and adiabatic. In isothermal, it is PV is equal to constant. In adiabatic, it is PV to per gamma is equal to constant. Gamma is your Cp by Cv. So specific heat at constant pressure divided by specific heat at constant volume. So those are about isothermal and adiabatic. Then isophoric, I was telling it's a constant volume. The volume remains constant. Isobaric bar term, the pressure remains constant. So for those two also we have studied work done. In isophoric there is no work done because the volume remains constant. So whatever heat you supply, it increases the internal energy. Okay, so then we studied about the heat engine, the refrigerator, then the heat pump, and we are deriving the equation of efficiency of a heat engine and efficiency of a refrigerator, which is otherwise called as coefficient of performance. Then we told that as per second law of thermodynamics, so that's till that point, till heat engine and refrigerator, whatever we studied, it was first law of thermodynamics. Then as per second, then we derived the expression for efficiency and coefficient of performance, and then we said that efficiency can never be equal to 1, or coefficient of performance can never be equal to infinity, because you cannot convert all the heat into work. So those are second law of thermodynamics. Now, uh, in your curriculum, the Carnot cycle is there. So how to find the efficiency of a Carnot engine? So Carnot engine, to know that Carnot engine is a ideal engine. So Carnot engine actually does not exist in reality. It's not a practical engine. It's a ideal engine. So it has two isothermal process through two adiabatic processes. So both four of these processes are reversible processes. Reversible processes. Reversible means what? You come from one state to another state. You go and you should be able to come back to the original state also. So that is possible in theory. That is a ideal thing, which is not possible practically. Okay. So Carnot engine is a ideal engine where the efficiency of a Carnot engine is maximum, but not one. Okay, efficiency can never be one. So efficiency of a Carnot engine is maximum, but not one, because because of second law of thermodynamics. Okay, even if you make all the processes reversible, still you cannot make the efficiency one as per second law of thermodynamics. But a engine with all the processes reversible is the engine with highest efficiency. Okay, so if you make the processes reversible, you can achieve highest efficiency, but not one. Okay, so now let us discuss about the irreversible and reversible process. Okay, so let us now I've drawn the PV diagram. Okay, so let us say a system or a gas or whatever it goes from a state I to state J. So let us say this is isothermal expansion. It is why it is expansion, because it is going from volume V1, it is going from volume V1 to V2, right? So V2 is greater than V1, right? So it is taking some heat and expanding. That's why it's isothermal expansion. So when it will become so, uh, let us say from I to J, it takes heat Q and does some work. It is doing some work because the area under this curve is nothing but the work done. So you are taking some heat and doing some work. So that's from I to J. Okay, so it does some work on the surrounding. So when something expands, it does some work on the surrounding, and when something gets compressed, the system does work on the surrounding. So I to J, it takes some heat, does some work on the surrounding. Now the question is, can we go from J to I? Like I have come from I to J. Can I go from J to I? If that is possible, if I, yes, if I can go from J to I, then it will be reversible. Okay. So let us see why reversibility is not possible. That we'll discuss. Okay. System and surrounding brought back to original state with no effect elsewhere. That is from J to I is called reversible process. So if you can bring back this gas to its original condition, suppose let us say because of heat exchange, the outside it has taken some heat. So when it is getting compressed again, here it has expanded. Now you are compressing it. If you are compressing it, here it is heat taking and work doing on the surrounding. Now it has expanded. Now if you are compressing, you will compress means work done on the, now you are doing work by the system on the surrounding. Now in compression, work done on the system by the surrounding, and during that process, when the work done by the system on the system by the surrounding, when it is compressing, that time it will give back the heat to the surrounding. And earlier it has taken heat, now it is going to give back the heat. Suppose during this process, it is compression and it will try to give back the heat. So when it gives back the heat to the surrounding, so can it be perfectly, can it be perfect so that the surrounding comes back to its original state? Let us say the surrounding was at temperature, some temperature, like at each point, at each point, at each point, at each point. So whatever was the pressure and volume, will it remain the same?
If it compresses, the temperature will be increasing.
So the if it compresses, the temperature will increasing, and because it is a isothermal wall, it will give back the heat to the surrounding. So when it gives back the heat to the surrounding, whether the surrounding can come back to its exactly original state.
At first initial state.
Yeah. Is it possible? And at each point, it should come back to original state, not only first and last. At each and every point, it should come back to original state. So that is not possible.
Yes.
So that's why that's its reversibility is a ideal situation. It is not a practical situation. I'll tell some more thing about it. Why is it not possible? Okay. So the example of irreversible process. What are the different example of irreversible process? Let us say petrol. You are in a petrol engine. Like the actually this petrol engine or diesel engine are otherwise called as IC engine or internal combustion engine. Whereas the railway steam engine is called external combustion engine because the coal is burning outside. So in this internal combustion engine is again divided into two types of engine, petrol or diesel. Petrol engine is otherwise called as SI engine. Okay. What does SI stands? SI stands for spark ignition engine. SI means spark ignition engine. Spark ignition engine. Spark ignition engine is nothing but your petrol. Petrol engine is a spark ignition engine. Similarly, this diesel engine is called as CI engine actually. CI. What does CI stands for? This is diesel engine. Your truck engine, heavy vehicle engines are all diesel. Okay. So CI stands for compression ignition engine. Compression ignition. Compression ignition. Okay. So diesel engine is otherwise called as compression ignition engine because in diesel engine you don't have a spark plug. The combustion gets initiated like you compress it. The compression ratio of CI engine or diesel engine very high. So you compress the air to such an extent that the pressure rises to such an extent that when pressure rises, temperature also rises. So when you inject the atomized fuel and that from the nozzle spray, the ignition automatically starts. So the ignition starts by compression itself. That's why that is compression ignition. Whereas in SI engine or petrol engine, you have to have a spark to initiate the ignition. So the compression ratio is less in case of petrol engine. So what exactly is compression ratio? Like let us say you have a piston, you have a cylinder, you have a piston. Okay. So let us say this particular there will be this is like let us say this initially your the total volume. Okay. Let us say the total volume initially VI. Okay. Then this piston moves and it goes to this condition. Okay. So this volume is equal to V2. This much, this little volume is equal to V2. Okay. So your swept volume, like not V2, Vj, let us say. So what is your swept volume of this cylinder? So Vj minus Vi. That is the swept volume. Swept volume. Swept volume means that piston moves, sweeps by that much direction. Yes. So that is swept volume. So that swept volume. What is compression ratio? That Vj, the final initial volume in Vi by final volume is equal to compression ratio. Compression ratio. So the compression ratio is nothing but the final volume Vj, because you cannot touch this piston cannot touch the wall because there will be some valves and all some amount of clearance will be there. That's why it is not touching the wall. Okay. So initial volume is Vj, final volume is initial volume is Vi, final volume is Vj. So that ratio is compression ratio. So 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 that's the compression ratio. Okay. Um, and swept volume. When you say like, okay, my vehicle or my car is 150 cc or 1200 cc, what does that mean? Cc means centimeter cube. Okay, 1 centimeter cube is equal to 1 ml. Okay, so when you are saying that my car is say 1500 cc, that means it's swept volume. This swept volume, this amount, this volume is your swept volume. Okay. So this swept volume, that is like my when we define the specification of a engine, we say what is the swept, what is the how much is the cc, how much is the cc? Like cc means your centimeter cube, which is nothing but your ml. So 1500 cc means it is 1500 ml. So bigger is the swept volume, more powerful is the engine. So truck or car, they will have much more powerful engine as compared to two-wheeler, like scooter or this thing. So their swept volume is lesser. Okay, so that's how it is. Okay, so that's about. So I was talking about the irreversible process. So when petrol reacts with air in petrol engine, you get a gas. So you know the combustion equation in chemistry. The petrol will have either methane or ethane, whatever, hydrocarbon. Okay. So that hydrocarbon or that organic compound, it will react with air. Okay. So air has 78% nitrogen or 20% oxygen, and rest other gases remaining are other gases, right? So when petrol reacts with air, you get some gas and some heat energy is released. So what is this gas? It can be carbon dioxide or if the combustion is incomplete, you will get some carbon monoxide. And if the petrol contains some sulfur, you will get sulfur dioxide, which is very, very undesirable gas. Even carbon monoxide is very, very undesirable. Carbon dioxide is a greenhouse gas. So all these things you need to avoid. But anyway, this combustion creates some undesirable gas, which creates pollution. So the fuel plus air with the help of spark. In case of petrol engine, you need a spark to suddenly rise the temperature so that combustion takes place. Okay, so that one, it will create a gas, and in terms, it will create energy. Energy will get released, and you will create other gases like energy plus carbon dioxide. So air, which is otherwise oxygen, it helps in combustion. Okay, so your methane or ethane, it isn't a combustible matter. Air helps in combustion. You provide a spark, the combustion starts, it generates some energy and some gases. Okay, so this what happens because of the spark? All of a sudden, the pressure and temperature increases because you are giving some heat energy. All of a sudden, you are putting some heat energy there. So when you are putting heat energy, so let us say it is getting compressed here. So after it is getting compressed, there will be, it is already compressed. That means it's a high temperature, high pressure air already. So when it is high pressure and you are injecting fuel there, all of a sudden combustion starts. When combustion starts, some heat energy is getting released. So you are adding some heat there. So if you add some heat there, then the pressure and temperature of that particular gas increases. There is a sudden explosion happening. So in a air fuel mixture, if you suddenly you ignite it, the pressure and temperature will increase, and it will try to expand it. So that's sudden expansion because pressure temperature all of a sudden increases. So it will try to push down the piston downward. Okay, so that's called the power stroke. Okay, that's called the power stroke of the engine. So in the we extract the work in the power stroke mostly in an engine. Okay.
Yes.
Okay, so this particular process, that combustion, petrol plus air combustion, that is a irreversible process. So you have air, you have petrol, you have created some gas. Can you bring back the gas to air and petrol again?
No.
Not possible. So that's why it is a irreversible process. Okay, and then another example of irreversible process is cooking gas diffusing into room. So suppose because of some leakage or so, the gas is getting diffused into the room. So in that case, can you bring back the gas again into the cylinder?
No.
Not possible. Similarly, you have a say you have a reservoir. So you have a reservoir. So you have a let us say a stirrer. Okay, a stirrer. Okay, so that liquid is being stirred in thermal reservoir. This liquid in thermal stirring of liquid in thermal so this liquid is in thermal contact with this reservoir. So you have a liquid here, this is a stirrer and this thing. So when you are stirring it, you are putting some energy into it. You are doing some work. That work is getting added to this liquid. Liquid will get heated if because of the work done. So that heated liquid will again transfer that heat to this vessel. Okay. So so can we again this heat has already gone to the vessel. So can we get back that heat and bring back the liquid into the original position? Not possible because your work has already got converted into heat. So again, you cannot convert that heat into work again because heat cannot be converted to work 100%.
Yes.
That's the law of second law of thermodynamics. So you cannot, because of second law of thermodynamics, once you convert work into heat, heat cannot be converted into work exactly 100%. As per second law of thermodynamics. That's why it's a irreversible process. Okay. So, so irreversibility is a rule, but not practically feasible. So it's an ideal thing. So irreversibility is not practically feasible. Okay. So what are the different causes of irreversibility? Why in the practical world, why irreversibility? Why these processes are irreversible? Okay. The reasons are like uh, so explosive chemical reaction taking system into non-equilibrium state. So when this combustion is happening, so all of a sudden you are putting a spark. Within seconds it will get expanded. The lot of heat will get generated and expansion takes place. So with such kind of system, it will not be like each and every step from, let us say, the gas, the air was at some temperature. Now it has become a gas at, say, the air was at, let us say, compressed air was at 200 degrees centigrade. Because of heat release, it has gone to 4000 degrees centigrade. So it is not possible to bring that gas from 4000 gas to 200 degrees centigrade air. Impossible. So that's why, because and each and every stage within seconds it has happened. So when it is happening within no time, you are not allowing the system to go slowly. So equilibrium can only be achieved when it is going from here to here. You can try to achieve equilibrium if you do it slowly. That is called almost static. That is called quasi-static, infinitely simul process, which is very, very slow. So when you go very, very slow, almost static, then only you can achieve a state of equilibrium. But in this case, when you are explosion is happening, it is not a you cannot achieve equilibrium. Okay. So yeah, so explosive chemical reaction is a reason behind non-equilibrium, non-quasi-static. That's why you cannot bring the system to original position. Then what are the other things that are present in nature? One is your friction, another is your viscosity. So, now, so okay, these are all dissipative processes. Okay, so moving body coming to stop, heat generated by friction goes to floor. So, so let us say we have the floor and we have a moving body, and let us say it is moving. Okay, but between this floor and the body, there is a friction acting. Let us say coefficient of friction mu. So because of the friction, at some distance it will stop. Otherwise, it will move. If there is no friction between the floor and the body, it will keep on moving. So, as per first law, you know that unless you apply external force, the body will keep on moving with uniform velocity, or it will maintain the state of rest. So, if it is moving at 100 km per hour, it will keep on moving at 100 km per hour without pressing the accelerator or even anything. But because there is a friction between the wheel and the road, without putting additional gas or additional fuel, it will stop. So when it stops, the energy, the kinetic energy of the body is becoming zero. That is getting converted into heat energy. Okay, and that heat is going to the floor. So, so when the already it has gone to the floor, work can become heat, but heat cannot become work completely, 100%. It cannot. So you cannot. And so that is one reason behind irreversibility. Okay. Similarly, viscosity. You might we have studied in liquidity. There is something called viscosity, which is almost similar to friction in solid. Okay. Yeah. So viscosity, when a pressurized fluid flow through a pipe, there will be something called frictional loss. Okay. So that frictional loss, uh, actually, that depends on the viscosity. Okay. Um, I think something I remember we study that like that frictional loss or frictional head loss is equal to something like FLB square by 2D or something. Some frictional loss is there. Okay, so when a pressurized fluid is passing through the a pipe, there will be a frictional loss. Like whatever is the pressure here, like at end A, at end B, at the other end, you will not get that kind of pressure. There will be pressure loss. That is called frictional loss. Okay. that depend on the length of the pipe, that it depend on the diameter of the pipe, like FL V square by 2D or something. I just don't remember that formula. We can brush up. So it longer is the pipe, longer is the pressure lock. Higher is the velocity in the pipe, higher is the pressure drop. Similarly, this is not D. Okay. The lesser is the diameter, more is the pressure drop. So this is called coefficient of friction in the pipe. So that depends on the viscosity of the fluid. More is the viscosity of the fluid, more is the friction in the pipe. So viscosity in liquid is something similar to friction in solid. Okay. So because of presence of friction, viscosity, and other dissipative process, moving body coming to stop, heat generated by friction goes to the floor. So it goes to the floor. Once it goes to floor, heat you cannot convert to work. Okay. Similarly, rotating blade stop due to viscosity losing mechanical energy. So a rotating blade, when it is rotating inside a liquid, it can stop because of viscosity, because of friction. See, something is rotating because of friction, like say a turbine, a wind turbine is rotating because of the friction with the wind. Slowly it will stop. Similarly, if a hydro turbine is just rotating inside liquid, because of viscosity of the friction, it will stop on its own. Like the solid friction, a car is stopping. Similarly, a turbine is stopping. The one is in one case it is friction with the solid floor. In another case, it is the friction with the liquid. Okay. So because of all these things, rotating blade stopping and other things. So because of all these uh, causes of irreversibility present in the system, the process cannot be reversible. Okay. So dissipation can be minimized, not eliminated. So whatever heat is going to the floor, it can be minimized, but it cannot be eliminated. That's why it is irreversible. Okay, because of the presence in friction, because of the presence of viscosity, because of these things present in nature, the process cannot be irreversible. Okay. So reversible means conversion of entire heat into work. Okay. So this one stirring the liquid. So you are putting some work that goes as heat into the liquid, get transferred to the vessel. So so but it is a irreversible process because it cannot be reversible, because if it is reversible means conversion of entire heat into work. Suppose you want to bring back this liquid to the original temperature. So that is conversion of entire heat, whatever absorbed by the vessel into work, which is not possible because of second law of thermodynamics. Okay. So finally, what does it mean, like uh, practical engine, reversibility? Uh, um, so in practical engine, there is the processes are irreversible in practical engine. Okay. So to make it reversible, the system has to go each and every step from I to J. Every point it has to be quasi-static. It has to be equilibrium with the surrounding, which is not possible. So to achieve reversible process or ideal process, you have to have quasi-static equilibrium. Okay. So with surrounding, which is not possible. Okay. Okay. So isothermal expansion of ideal gas in a cylinder with so another example of reversible process is isothermal expansion of ideal gas in a cylinder with frictionless piston. Okay. So if this piston, this is the piston actually. So if this piston with the cylinder there is no friction, okay, then only it will be possible. So it is here isothermal expansion is happening, the piston is going down, but if there is no friction between the piston and cylinder, then only it will become it can become a reversible process, but it can never so happen that you will not have friction. Okay. So the takeaway is in practically there are many sources of irreversibility, like friction, like viscosity, And like the process of explosion, it is very difficult to bring it back to the original
Original
condition. And when a body moves, there will be friction, the heat get dissipated and get absorbed by the floor, and it cannot be brought back. So because of presence of friction and this thing, the irreversibility is not possible. Okay. So then why you are studying why if irreversibility is not possible and no process is reversible, then why are you talking about reversible process? Because in second law of thermodynamics we have told the efficiency can never be 100%. But what is the maximum efficiency? That is the maximum efficiency is possible only when the processes are reversible process. So those ideal processes, so a engine containing ideal processes will have maximum efficiency. So it will not be one, but the efficiency will be highest. And a practical engine will always have lesser efficiency than an ideal engine. Ideal engine contains reversible processes. So a ideal engine like Carnot engine contains reversible processes, and the efficiency of a Carnot engine is maximum, but not one. If it is one, it will disobey second law of thermodynamics. Okay, so that's all about reversible and irreversible process. Then we'll discuss about the Carnot engine with a basic understanding of reversible process. Okay, thank you.